Okay, so what is the length of each side of the cube container holding the gas in L1 that had an internal energy of 7,732 joules, assuming the pressure inside was 1,952,470 pascals. And so you can first derive that and then solve that. So go ahead and pause the clip and give that a try, and then when you're ready to check, you can hit play to continue. Okay, so we've got our gas, 3/2 PV, and we can place our values in there. So we should get a volume of 0.00264 meters cubed, if that's the situation there. So if we look at the length, width, the height with that, we're dealing with 0.138 as the length of each side. So about 13.8 centimeters for each side. All right, so when we talk about conservation of energy, including internal energy, again, it's looking at the total amount. And so now we have to consider what's happening, right? And so in this case, with non-conservative work, we know with non-conservative work that deals with friction or air resistance, anything that's affecting the overall energy of the system. And that's what we need to consider now is the change in internal energy. Is some of this mechanical energy turning into internal energy, those molecules shaking faster because of what's going on there. So now when we're dealing with this, we can include that within our conservation of energy equation and evaluate what's going on. And so we'll take a look at that in this situation. Let's say we have this Joule apparatus where we have the mass is hanging from both sides, and then they're going to be falling, spinning the paddles. Something that we want to consider with this is that the mechanical energy that we have, this potential energy, is going to turn into internal energy. It's going to spin those paddles. So when we consider that, in this one here, we have the mass of 11.5 kilograms. We have a height of 1.3 meters for these. We figure out how much energy is transferred to internal energy. Well, in fact, and if it's perfectly insulated, right? So what ends up happening is, no energy is transferred out as heat, and so therefore all this potential energy should turn into internal energy. Now the paddles are going to be spinning, and that's kinetic, but all that kinetic energy is going to turn into internal. So when we take a look at this one, all of that potential energy is going to turn into internal energy. And so there's no final height, right? The final height is 0. We have our initial height. We have our speed of the paddles, is all going to be taken up then into the spinning of the water itself. So we've got that there. So all that potential energy will turn into internal energy. So therefore, the increase of internal energy be 146.51. So let's say inside here, let's say it was already at 1,000 joules, and this amount of energy would come into it, then the final energy 1146.51, right? And so an increase of energy there. All right, so in this example, we have a bullet going and hitting a wooden block fixed in the ground. Bullet passes through the other side with a speed of 25 meters per second. If we ignore the small amount of gravitational potential energy, find the internal energy of the block bullet, and I should say increase in internal energy of the block and bullet after the impact. So yeah, so why don't you go ahead and pause the clip here and see if you can think through this and work this out with your non-conservative work equation that's a little bit modified now with the conservation of energy, and give that a try. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so we're going to need our mass in kilograms for this bullet. And if we evaluate the energy, right, you have a kinetic energy starting out 255 meters per second. Then afterwards, that bullet continues on with 25 meters per second, but it slows down considerably. And because it slows down, that energy had to go somewhere, and that goes into increasing the internal energy of the system. So when we set this up, there's a small amount of gravitational potential energy change, negligible. So we can leave that at 0, and then we have our kinetic energy changing and relating to the change in internal energy. And so we've got the difference there, and we'll end up getting a internal energy increase of 805 joules. So that would be the increase in the internal energy of the block as well as the bullet itself too. So, considering all of the internal energy increase of both of them. All right, so let's say we have a airplane that's landing here with an initial velocity or initial speed of 57 meters per second, and the landing distance, the time or the distance it takes for the airplane to come to a stop is 1,829 meters. And we want to find out what is the non-conservative work here, and then what's the force of friction. So we'll do that. So go ahead and pause the clip, and this will be good practice using that and good review. And then when you're ready to check, you can hit play to continue. All right, so non-conservative work equals a change in gravitational plus a change in spring plus a change in kinetic, right? So in this case here, there's no springs involved. There's no actually gravitational energy involved. And so if it's flat, so we're just dealing with the change in kinetic energy, starting with 57 meters per second going to 0. So there's our non-conservative work. And therefore, we have force of friction over that displacement, so we can figure out how much friction there was there. And so 1829 cosine of 180, right? Because the the airplane is going this way, friction's this way, cosine of 180 degrees. This is -1. And so we have a force of friction of, let's see, 21,352.98 newtons. And then what is the increase in internal energy? Well, it actually is this, right? That's how much non-conservative work there was in joules. And so all of that non-conservative work, that friction there, went to increase in the internal energy of the system. So in this example, we have an acorn falling from a tree, landing on the ground 10 meters below with a speed of 11 meters per second. So in this one, we want to find out what is the average work done by air resistance during the fall. And then part B, what is the average force of air resistance during the fall? And so, yeah, go ahead and set this one up and give this a try. And when you're ready to check your answer, hit play to continue. All right, so the key with this is recognizing you have potential energy starting out. All that potential energy is being transformed into kinetic energy, and there's no springs involved, so we've got that. The total non-conservative work then is -3 joules, so that's the total amount of work done against air resistance, or work done against the ball as it goes down, and that's the work done by air resistance there. And then to find the force, we know that the non-conservative work is the force of friction times displacement times cosine of 180. The motion is downward, right? The ball is moving downward, but the upward air resistance is fighting that, right? So 180 degrees is so cosine 180, and we get for friction 0.3 newtons. Okay, so I want you to imagine we're on a path, and we find this rock, and we want to know what this rock is. What we can do is we can visualize energy transfer, and then be able to, determine the substance of different things and be able to evaluate the thermal transfer from one object to another. And so we can figure this out using a very helpful equation here, Q equals mc delta T. The specific heat that we're dealing with here is the amount of heat required to change the temperature of materials proportional to mass and the temperature. So Q is heat in joules, mass in kilograms, specific heat capacity C, and then T is the temperature change. So specific heat capacity then is the amount of heat required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. So for instance, if we had a beaker 1 kilogram, which is 1 liter of water in here, right? And we put heat into it, it would take 4,186 joules for the temperature to increase by 1 degree Celsius. Therefore, C for water is 4186 joules per kilogram degrees Celsius. And each substance has a certain amount of specific heat capacity. So metals and different other things, right? And really anything has a certain amount of specific heat capacity where you have to see how many joules are there, like in this case, how many joules does it take to increase the temperature by 1 degree Celsius. If you had a 1 kilogram mass, probably equivalent in size like this to that, 1 kilogram of that, it's not going to take nearly as much joules to make that increase by 1 degree Celsius, right? And so it has a much lower specific heat capacity. Here's a table of them. In the middle column, it's the kilocalories for grams or kilograms. I'm going to cross through that. We're really going to be using, for the most part, joules per kilogram degree Celsius. So in other words, if you had a block of ice, turns out ice is different than liquid water. It takes 2,100 joules to increase by 1 degree Celsius if you have 1 kilogram of ice. If you have a kilogram of aluminum, so a kilogram of aluminum like this, if you put 900 joules into it, it's going to increase the temperature by 1 degree Celsius. And you could look at some of these other substances here. Lead, it only takes 130 joules for each kilogram of lead to make an increase, very low specific heat capacity. Liquid is on the high end here, right, 4,186. And then, other metals are in between. And then, they even include like proteins here, and then the human body, which we have made up of a lot of water. So how much heat would it take to raise the temperature of 1.5 kilograms of copper from 19 degrees Celsius to 25 degrees? So this is another form of the same equation here, just rearranged a little bit. So Q equals MC delta T. And we're just, if you divide mass and temperature to the other side, you get C equals Q over M delta T. Same thing. And so, yeah, go ahead and use this chart and use the amount in joules per kilogram degree Celsius to, figure this out for copper here. And when you're ready to check, you can hit play to continue. Okay, so we should get a value of 3,510 joules as how much energy it would take to increase the temperature from 19 to 25 degrees Celsius. Delta T, remember, it's final temperature minus initial temperature. And then, you have your mass here in kilograms, and then this is the specific heat capacity, 390.